Hello, everyone. Can you hear me, all of you? Okay, so let's see. Okay, so welcome to the session on Mathematics Olympiad program at chinta.com. We will be discussing a little bit of geometry today. And so this is geometry for Maths Olympiad. And one of the things that we will be talking about is known as the Mickle point problem. The Mickle point problem. It's a very beautiful problem from geometry, the Mickle point problem. So the way you think about it is actually like this, that if you have a triangle, it all starts with a triangle, I guess. If you have a triangle ABC, so you have 3 points A, B, C, and you pick points D, E, and F from the sides of the triangle. You pick the points D, E, and F from the 3 sides of the triangle. And you want to draw circles on the triangle. Okay. So I see that many of you are looking into this from YouTube and Facebook as well. Okay. Great. So if you do not know, if you're joining this or tuning in for the first time, this is the training session for the Maths Olympiad coming up in the month of July, the Bose Maths Olympiad. And you can go to chinta.com/Bose to access the registration page of this. Okay. Great. All right, so what do we do? Well, we take the 3 points B, F, D, these 3 points B, F, D, and we join them in a circle. You take the 3 points B, F, and D, and you draw the circle that passes through these 3 points. So through any 3 points of the triangle, through any 3 points which are not passing through the same line, you can always draw a circle. You can always draw a circle like this. So I draw the first circle is BFD. BFD is a circle. And then I draw another circle AFE. So this is circle 1. This is circle 2. Okay. Now I am tempted to draw the third circle. I am tempted to draw the third circle CED. So I want to draw, draw circle CED. This is the circle that I want to draw. This point is M, suppose. The point where the red circle and the green circle actually intersected, that point is M. I want to draw the circle CED, but you know what will happen if you draw the circle CED? If you draw the circle CED, it will pass through, well, at least we can try to show that, it will pass through the point M. If you draw CED, it passes through M. This is the claim. This is what we want to show. So maybe I can, this is something that we want to show this. This is the goal. So we want to show that, okay, maybe I just zoom in a little bit. Okay, here we go. So if we have A, B, C, a triangle, and if we pick up 3 points, D, E, and F from the 3 sides of the triangle arbitrarily, then BFD and AFE, if we join these 2 circles, they will intersect at a point M. We want to show that the circle CED also passes through M. That's the main question that we want to answer. How can we say this? Now there is a subtlety of this problem. Let's look at this. There is a subtlety. So the subtle idea is this, that if you have 4 points in the plane, there is no guarantee that a circle will pass through all 4 of them. It is not guaranteed. We do not know that there is a circle that passes through all 4 points. It's a very special case when a circle passes through 4 points. If you draw a circle, if you have 3 points, you can always draw a circle through them. If you have 3 points, you can always draw a circle through them. But if you have 4 points, then that might not be true. You might not be able to draw a circle through all of these 4 points. When the 4 points lie on the same circle, let's say point 1, point 2, point 3, and point 4, when the 4 points lie on the same circle, P1, P2, P3, P4, on the same circle, if 4 points lie on the same circle, they are called concyclic. It's a fancy name. They are called concyclic. But the good thing is that if you have 3 points which are not on the same straight line, you can always draw a unique circle through them. So you should be learning this in the geometry module of a Math Olympiad program. That you can always draw a unique circle through 3 distinct points. So, but for 4 points, this is not guaranteed. That's why our problem is kind of special. Why is it special? Because we have 4 points here. The 4 points are C, E, D. These are the 3 points. There is always a unique circle passing through these 3 points. What we claim is that this circle will also pass through M, the intersection of the first 2 circles. That's what makes this particular thing much more interesting. Okay. Now, how do we show that this is true? So what is the property of a cyclic quadrilateral? That is, if 4 points are concyclic, then you can join them to create a quadrilateral. That is a cyclic quadrilateral in some sense. Yes, Ishan is right. So let's join these points and let's see what we can do. So what I'll do is I'll just shade this one in white. This is, we know that these 4 points all lie on the same circle. That's almost by definition. That's true. And we also know that these 4 points lie on the same circle. So the red one is a cyclic quadrilateral and the white one is also a cyclic quadrilateral because all the 4 points lie on the same circle. That's the reason they are cyclic. One good thing about cyclic quadrilaterals is this, that opposite angles will always add up to 180 degrees. This is the property that we will be using. that what is the property? Maybe I can write it. If you have a cyclic quadrilateral, then if you add the two opposite angles, this one and this one, angle 1 and angle 2, if you add angle 1 and angle 2, then they add up to 180 degrees. So there is a proof of this fact that sum of the opposite angles of a cyclic quadrilateral is 180 degrees. And you should not accept this kind of statements without proof. But unfortunately, this is just a seminar. This is not the main course. So we cannot really talk about the proof here because this is a very simple and yet a beautiful proof. It's available almost everywhere. So you should go up and try to do this on your own. We will be using this property directly to solve our problem. So what is this property? What is this property? So here is the property. So the property is that if two opposite angles of a quadrilateral adds up to 180 degrees, then it is cyclic. Actually, the other thing is also true. If it is cyclic, then the opposite angles will add up to 180 degrees. That's also true. So both of them are actually right. Okay, that's great. So if we can show that the opposite angles of this particular, okay, maybe I can move this, throw this out, pull it down, and zoom it in. Let's do that. Okay, so what do I want? Well, I want to show that CDME is a cyclic quadrilateral. That's what I want. I want to show that CDME is a cyclic quadrilateral. To do that, if I can show that the opposite angles add up to 180 degrees, then we are done. So can anyone show that opposite angles will indeed add up to 180 degrees? It's not hard. You can think and do this actually on your own. But while you try this, let me tell you what is surprising about this problem. You know, every problem has, a good problem has that element of surprise, something that hits your mind. Okay, this is happening. Oh my God, this is very nice. This wow factor of a problem is what makes it so beautiful. So the wow factor of this particular problem is that you can choose the points D, E, and F almost randomly. When you started off with these points D, E, and F, it does not matter which 3 points you choose. This particular property will always hold. So that's why this problem is so, it's simple, but it's beautiful. It's simple, but beautiful. Okay. Now, if you look at this particular picture, you'll see that this is not actually hard. This is actually very simple. Can anyone tell me what is the value of this particular angle? The one that I have shaded in green. Can you tell me what is the value of the angle DMF? What is the value of the angle DMF? Use the fact that BFMD is a cyclic quadrilateral. Samir, they are D, E, and F. They are like 3 points from the sides BC, CA, and AB. These 3 points. D, E, and F. These 3 points. Yes. So you can select them as you wish. Yes. Okay, so what is the value of angle DMF? It's not hard. It's not equilateral. Okay, but I see what Shreya is saying inside the class. It's 180 degree minus angle B. Do all of you agree on that? This particular angle DMF is 180 degree. This angle DMF is 180 degree minus angle B. Do you agree on that? Do you see why I'm saying this? Because this BFMD is a cyclic quadrilateral, so the opposite angles should add up to 180 degree. This is B, so this must be 180 minus angle B, right? Okay, so this is 180 minus angle B. This is 180 minus angle B. Using the same idea, can you find out this white angle? Using the same idea, can you find out this white angle? Right down here. This white angle is what? A similar idea should help you to find out this particular white angle. Could you find that? Excellent. Ishan is correct. Very good. This is 180 minus A. So we have two angles, 180 minus B and 180 minus A. Now we are ready to find out the third angle, which is this one. So angle DME. So we have this angle as 180 minus B. This is 180 minus A. So what is this remaining angle? What is this remaining angle? Well, if we can show that this is 180 minus C, then we are done, because this is C, this is 180 minus C, then they would add up to give 180 degrees, which is basically what we want. We have to show that this is, yeah, this is relevant for PRMO as well, Asha. That's correct. This is for Maths Olympiad in general, yes, but also for PRMO, sure. Okay, so what we will do is, this total angle right here is 360 degree. This total angle is 360 degree. We will subtract from it 180 minus B and 180 minus C, those two other angles. We will subtract from it 180 minus B and 180 minus C. You're right, Samir, you're correct. Very good. So then this turns out to be what? Let me just squeeze this a little bit more. Okay, here we go. So this turns out to be 360 minus 180 plus B minus 180 plus C. So this is angle B plus angle C. So this angle right here, this turns out to be angle B plus angle, sorry, this is what? This was A, right? Angle B plus angle A. But angle B plus angle A, this is A plus B, and then this one is C. So A plus B plus C, we know that's 180 degree. And we are done. In that quadrilateral, in this particular quadrilateral, this angle is angle C, this is A plus B. So A plus B plus C, so that's total 180 degree, and we are done, right? So we have proved that CDME is a cyclic quadrilateral indeed. Okay, that's great. So Once we have done that, we are ready to talk about the Mickle point problem. So let's look at this. The Mickle point problem is actually very beautiful. In fact, you can call this M a Mickle point in some sense. But the actual problem is like this, that if you have a quadrilateral, okay, maybe I can draw it like this. Maybe I can make a little bit more space. Okay, here we go. It's a very beautiful problem, by the way. You have a quadrilateral like this. Any quadrilateral, this particular quadrilateral may not be cyclic. If it is cyclic, then you have many more beautiful properties. But maybe this one is not cyclic. Maybe this one is not cyclic. So what you do is, cyclic means the points are on the same circle. So maybe this one is not. So you have A, B, C, D. Now what you do is you extend AD and BC. You extend AD and BC like this to meet at a point. You also extend BA and CD to meet at a point. Okay. So this is, suppose this point is X, this point is Y. Okay. Great. So what you do is you start drawing circles. So first two circles are kind of simple. You draw this one. And you draw another one like this. So you have drawn two circles and they will intersect at a point. Let's call this point M. So no problem so far. This is fine. What we want to do is that we want to show that we can draw more circles in this and they will also pass through the point M. I just want you to pause and think about the entire picture. This is, so AY is not equal to AD. That's not given. That's not given. So I will be drawing more circles now. Maybe I can change the color a little. Oops, what is this? I don't know what just happened. Not sure what happened. Okay, maybe I can clean this up a little bit more. Something weird happened here. Okay, so quickly, let me draw the picture one more time. So this is, we have a quadrilateral like this. So we have A, B, C, D, and we extended these two to meet at a point X. We extended these two to meet at a point Y, and we drew two circles like this. Right? We drew two circles, not very pretty, like this. Well, they will intersect at some point. Let's call that point M. If they intersect at some point, let's call that point M. Okay. So I'm not saying M is a special point. Exactly, Obishruta is right. We have just named it. Correct. Very good. It's any point where the circles will intersect. Okay. All right, that's great. Now, let's draw two more circles. Let's draw two more circles. So one of them will be passing through, will be the circumcircle of BYC. So BYC, this particular large triangle right here. this particular triangle. So this circle will somewhat be like this. But the great news is that this circle will also pass through M. This circle will also pass through M. And this is a non-trivial fact. This is a non-trivial fact. You have to work hard to actually prove this. That the circle, the circumcircle of BYC actually passes through M. Not only that, the circumcircle of ABX will also pass through M. Something like this. So now you have 4 circles here. Now you have 4 circles here, and all of them are passing through the same point. This is pretty special. This is something not, this is not trivial. This is kind of very, very special. So, of course, we want to show that this is something that will definitely happen. But even before doing that, let me show you the picture in a little bit more sort of interesting way. So what I'll do is I will be, okay, so I'll do this like this. Okay, so I will go back to the, oops, sorry. I'll stop the share here and I will be going back to this picture. Okay, so here we go. Okay, here we go. So I will be sharing this screen right here. Okay, so now I think you can see it. Wait. And okay. Okay, so I will put this here. Okay, now I think all of you can see this. Ha, this is nice. So what is it that we are trying to do? Let's see. This is quite beautiful. We have this, so we'll start with the Polygon tool in some sense. So please don't write on the board, anyone. Okay, thank you. So I will start with this A, B, C, D. Please do not write here. Anyone, please do not write here. Okay, so this is fine. So I just do new points. Okay, now I just put the annotate creator. Wait. Okay, so that's what we have here. Right, here we go. So let me use the, oops. Let me use a line tool here. So what do I want? Okay, I want this AD and this BC to meet at some point. That point is here. That point is X. Yeah, let's say call it E rather. Actually, I don't want these labels to show up. And just let this labels go. By the way, you can also download this software. It's a very beautiful software. You can download this. This is very useful for making geometry drawings, but it's also quite useful for your for experimenting a little bit with geometry. So it's kind of nice. You can always do this. All right. And in fact, I can just get rid of the grid. I don't need that. I don't need the grid either. So just to make this thing a little bit more clean. Okay. Here we go. So we have this. Okay. So we have this intersection, and then we can draw another intersection, which is BA and CD. This is the other intersection. And what we will do is we will mark that point as well. So that's F, right? Okay, now let's draw a circle FAD. Let's draw a circle through the points A, F, and D. So that's the first circle. Remember, that was the first circle that we were interested in. And let's draw the second circle, DCE. So these were the two circles that we were interested in. These were the two circles that we were interested in. Right? Okay. So that's great. Now, we are also interested in another circle. So what is it that we were saying? Okay, let's mark this point here. This is the intersection point. So this point is M, suppose. So I'll just rename this as M, just to remind ourselves that we are actually working with the same point. We are working in the same context in some sense. Right? We are working in the same context. Right. Great. Now, what I want to show is that this FBC, this particular triangle, if I draw a circle through that, that will pass through M. But first you have to appreciate that this is a non-trivial fact. 4 points may not be always pass through the same circle. That's a very non-trivial fact. 3 points, through 3 points you can always draw a circle if they're not on the same straight line. But through 4 points you may not be able to do that. So I'll just draw the circle FB. So I want to draw it through C. Just check how it snaps to M. You see how it snaps to M? This circle that we just drew. It's quite beautiful actually. Maybe I can just change its color to red. It's a little bit slow, I guess, but here you go. So maybe I can change the color. Yeah, so that's red. Okay, now I will draw another circle through A, B, and E. Through A, B, and E. And that circle will also pass through M. That's a claim, A, B, and E. So let me draw that. I'll simply draw it through A, B, and E. And you'll see how it snaps to M. Right? This particular circle also snaps to M. So I can just change the color. So maybe this is green. Okay. And I mean, maybe I can change the color of this one as well. So this is probably blue. So we have 4 circles, the blue, the red, and the green, and the black. All of these 4 circles are passing to the same point. You see, this is quite beautiful, isn't it? I mean, this is not trivial at all. This is not trivial at all. This is it's a very non-trivial fact that all of these circles pass through the same point. If you have 2 circles, if they intersect, they will pass through 2 points. If you have 3 circles, there is no guarantee that all 3 of them will pass through the same point. But now here are 4 of them. Okay, so now let me do one thing. I want to motivate a particular type of visualization. So focus on the lines FM and EM. Just focus your attention to the lines FM and EM. Focus your attention to FM and EM. Okay. Now see what I'll do. I will move D and check what happens to these lines FM and DM. So I just sort of zoom in a little bit more. So check what happens to FM and DM. So, okay, so check, okay, look at this. FME is sort of like this. It's kind of at an angle, right? FME is kind of at an angle, but you can do something about it. You can, so if you want, you can make this into a straight line. So you can sort of flatten the angle. Now this is the part of the imagination. You have to imagine this. This angle is getting flattened in some sense. So how is it happening? You see, so FME was like was at an angle. What I'm doing is I'm sort of opening up this angle into a straight line. I'm opening up this angle into a straight line. How am I doing this? There is some magical thing I'm doing with this ABD. There is some magical thing. So this, I'm moving the point D, and in some way, at some positions, it's this FME sort of flattens. So I'll tell you the position. What I'll do is I'll draw a circle through ABC. Okay, I'll just draw a circle through ABC. Notice this circle through ABC. What I'll do is I'll move the point D, and as I move it to this point in the circle, as if D goes into this circle, okay, maybe I can just change the color of this circle so that you can see there's too many circles here. Red, and maybe I can change the style, line thickness, maybe 11. Okay, now let's see. So you can see the red circle, right? The circle, oops. The red circle that is passing through ABC. What I'll do is I will move the point D such that the red circle sort of snaps to the point D snaps to the red circle. So I'll move it. Move wherever I want. But as long as I am on this same circle, the red circle, you see how beautiful this is? This is a straight line. FME is a straight line. If you keep this point D on this red circle, FME is a straight line. Yeah, this is some sort of a conformal map. You're right, actually. Something like that is happening here. It's not a conformal map, but it is sort of, yeah, it's a kind of map, of course. So it's actually a theorem that if ABCD is on the same circle, then FME is on the same straight line. So in some sense, you are mapping circles to lines in this transformation. Okay. So we will not really prove anything today because we just wanted to show you a bunch of stuff that is exciting. If you want to participate in the Bose Maths Olympiad, you can go to chinta.com/Bose to access the registration of it. We will stop out the seminar today here, and we will see you again next time at maybe in the same time. Thank you all for joining, and keep on exploring this picture, and I'll see you next time. Bye.